Imagine you are looking at a perfectly still pond. The surface is flat and smooth. Now you throw a rock into the middle. What happens? Ripples spread out from the center, disturbing the calm water. This is a simple picture, but it helps us think about something much, much bigger. In 1915, Albert Einstein gave us a new way to see the universe. He said that space and time are not separate things. They are woven together into a single four-dimensional fabric called space-time. And this fabric isn't just a boring, flat background. It can be bent and warped by massive objects, like stars and planets. This is what we feel as gravity. An object with mass tells space-time how to curve, and the curve of space-time tells other objects how to move. This is the heart of Einstein's theory of general relativity. A planet orbiting a star isn't being pulled by some invisible force. It's actually following a straight path through curved space-time. Think of a bowling ball placed on a trampoline. It creates a dip in the fabric. If you roll a marble nearby, it will circle around the bowling ball, following the curve. This simple analogy shows how gravity works in Einstein's universe. It's a beautiful and profound idea that changed our understanding of everything. Now, what if something really dramatic happens in the universe? Not just a planet orbiting a star, but something violent. Imagine two massive black holes, each many times heavier than our sun, spiraling into each other. They are moving at nearly the speed of light. When they finally collide and merge, they create a massive disturbance. This event is like throwing a giant boulder into that cosmic pond. It sends out powerful ripples across the fabric of space-time itself. These ripples are not like light or sound waves. They are vibrations in the very structure of reality. They are called gravitational waves. These waves travel outward from their source at the speed of light, carrying energy with them. As they pass through you, they stretch and squeeze everything in their path. They stretch and squeeze space itself. The effect is incredibly tiny. So tiny, in fact, that Einstein himself thought we would never be able to detect them. For 100 years, they were just a prediction of his theory, a cosmic whisper we could not hear. But in 2015, scientists finally did it. They detected the faint echo of two black holes colliding over 1 billion light-years away. This discovery opened a brand new window to the universe. The moment we could finally hear these gravitational waves, our imagination took over. It always does. Whenever humanity discovers a new force of nature, one of the first questions we ask is, can we use it? And often that question is followed by another darker one. Can we weaponize it? From the splitting of the atom to the power of lasers, history is full of examples. So it's no surprise that the idea of gravitational wave weapons quickly appeared in our stories. Science fiction writers and filmmakers love to take a real scientific concept and push it to its most extreme and dramatic limits. In stories, these weapons are often portrayed as the ultimate superweapon. Imagine a device that can create and aim gravitational waves. It wouldn't need to fire a projectile or a beam of light. Instead, it would manipulate the fabric of space-time itself. In a movie or a video game, you might see a gravitational wave weapon that can tear a planet apart from the inside out. It could create a focused ripple that shakes a starship to pieces, ignoring any shields or armor. The weapon wouldn't be destroying matter with energy. It would be destroying the space that the matter exists in. It's a terrifying and awe-inspiring concept. This idea taps into a deep human fascination with controlling the fundamental forces of the universe. It's the kind of power once reserved for gods. The ability to warp reality itself is a compelling plot device. It creates stakes that are higher than anything else. How do you defend against an attack that stretches and squeezes the very space you occupy? Science fiction gives us a playground to explore these what-if scenarios. It allows us to think about the consequences of incredible power without the real-world risks. The gravitational wave weapon is a perfect example of science-inspiring fiction in the most spectacular way. But this brings us to a crucial question. Is any of this real? Or is it all just fantasy? We know gravitational waves exist. We know they are created by some of the most energetic events in the cosmos. And we know they carry immense amounts of energy across the universe. So how big is the leap from detecting a cosmic whisper to creating a weaponized shout? Is it just a matter of technology and engineering? Or is there a fundamental reason why it might be impossible? To find the answer, We need to separate the science from the science fiction. We need to look at what we know and what the laws of physics really allow. To understand the science of gravitational waves, we must return to Albert Einstein and his groundbreaking theory of general relativity. Einstein showed us that gravity is not a force pulling objects together, but rather the result of mass curving the fabric of space-time. Imagine placing a heavy ball on a stretched rubber sheet. It creates a dip. This curvature is static if the ball is just sitting there. But what happens if the object is moving? Specifically, what happens if it is accelerating? Einstein's equations predicted that any accelerating mass should create ripples in space-time, much like a moving boat creates a wake in the water. These ripples are the gravitational waves we are looking for. The first, and perhaps most insurmountable challenge in building a gravitational wave weapon is the sheer amount of energy required. As we've seen, the universe generates powerful waves by colliding objects with the massive suns. The energy released in the GW 150914 black hole merger was staggering, converting 3 entire solar masses into pure energy in a fraction of a second. This means that a single black hole collision released more energy in less than a second than humanity has used in its entire history, multiplied by trillions and trillions. In fact, it released more energy than our sun will produce in its entire 10 billion year lifetime. Gravitational waves, however, are spectacularly inefficient at interacting with matter, and that's precisely why they are so hard to detect. They pass through planets, stars, and people almost as if they weren't there at all. This is the efficiency paradox. Another critical feature of any effective weapon is the ability to aim it. Unlike light, which we can easily focus into a tight beam with lenses and mirrors, there is no known way to focus or direct gravitational waves. How would you actually build a machine to generate gravitational waves on demand? No known material could withstand these forces. The object would instantly disintegrate into a cloud of plasma. This confronts us with the ultimate catch-22 of gravitational wave generation. To create strong gravitational waves, you need to play with black holes. But if you have the technology to create, contain, and collide miniature black holes at will, you already possess a weapon of unimaginable power. The black holes themselves are the weapon. Using them to generate gravitational waves to attack a target would be a needlessly complicated and inefficient step. It's like inventing a cannon that fires angry bees. One of the most spectacular myths from science fiction is the idea of a focused beam of gravitational waves, a gravity lance, that could be fired at a planet to cause catastrophic earthquakes or even shatter it completely. However, the reality of physics makes this scenario a pure fantasy. A physicist might calculate that you would need the energy output of a star-going supernova detonated within a few million kilometers of the target planet to even begin to have a noticeable geological effect. In the grand battles of science fiction, for every superweapon, there is usually a super defense. If an enemy has a gravitational wave weapon, a hero's starship might be equipped with gravity plating or a space-time distortion shield to counter it. This fundamentally misunderstands what a gravitational wave is. It is not something traveling through space, it is a wave of space itself. You cannot put up a barrier within space-time to stop a wave that is made of space-time. Another popular myth in science fiction is the tactical use of gravity manipulation to create gravity wells or interdiction fields. In this scenario, a device generates a localized, intense field of gravity, creating a deep pit in the fabric of space-time. According to general relativity, gravity is a manifestation of mass energy. To create a gravity well, you need a massive object. To create a deep gravity well capable of trapping a starship, you would need an object with the mass of a planet or a star. This myth gets the cause and effect of gravity backward. You cannot have the effect, the deep gravity well, without the cause, an immense amount of mass. The fear of new discoveries being turned into weapons is a recurring theme in human history. From the splitting of the atom to the development of lasers, our greatest scientific achievements have often cast a dark shadow. It is natural, then, to look at the immense power of colliding black holes and ask that familiar, worried question. But in the case of gravitational waves, we can be reassured. The science that makes them so difficult to weaponize is the same science that makes them such a revolutionary tool for understanding the cosmos. Their weakness in interacting with matter is a feature, not a bug. It allows them to travel across billions of light years, carrying pristine information about their violent origins. This is the true value of gravitational waves. They are not a blueprint for a weapon. They are a new sense for humanity. For thousands of years, we have studied the universe only through light, a form of electromagnetic radiation. Now we can listen to it. We can hear the symphony of space-time itself. Gravitational wave astronomy is allowing us to witness events that were previously invisible, like the merger of two black holes in a dark corner of the universe. It allows us to test the limits of Einstein's theory of general relativity in the most extreme environments imaginable. This is a gift of knowledge, not a threat of destruction. The quest to detect these cosmic whispers has pushed our technology to its absolute limits, leading to incredible innovations in lasers, optics, vacuum systems, and vibration isolation. These advancements have applications far beyond astronomy, benefiting fields from materials science to computing. The pursuit of this fundamental knowledge enriches us, expands our perspective, and reminds us of our place in a vast and dynamic universe. It inspires awe and wonder, which are far more constructive emotions than fear. The story of gravitational waves is a testament to human curiosity and our relentless drive to understand the cosmos. So when you see a gravitational wave weapon in a movie, enjoy the spectacle, appreciate the creativity and the way it pushes the boundaries of imagination, but know that you are watching science fiction, not a preview of a future arms race. The reality of gravitational waves is, in many ways, more profound and exciting. They are not a sword to be wielded, but a window to be looked through. A window that has just been opened, promising decades of incredible discoveries, as we continue to listen to the silent, epic story that the universe is telling us through the ripples in the fabric of space-time.